Hi, everyone. Welcome to the EDAM seminar session. We're going to get started so long. I think a few more people are still streaming in, but we're very excited to have you here. So we're just going to start with a brief introduction to what the consortium is, and then I'm going to hand over to Dr. Gina Chandli, who's going to talk through our first session, which is very exciting. Cool. We can see the thumbs up, so I'm assuming everyone can see our screen. So a brief introduction, I think a lot of you already know about the EDAM Consortium, but EDAM, which is the Ethiopian Data Analytics and Modeling Consortium, is a sustainable, locally led real-time health data to modeling to policy consortium in Ethiopia. We're operating across sort of a few pillars, but one of the biggest pillars of this is capacity building. And it's really about building national capacity in data analytics and modeling with a bit of a focus on AI and seeing how we can sort of really build national on-the-ground capacity. And so this seminar series is falling within that. It's the first time we're conducting the series. So it's also going to be a bit of a learning process for us. We have 3 sessions across the next 3 days. The first being an introduction to modeling, the second being an introduction to AI, and then the third focusing on really how you get your data ready to use these techniques. There'll be feedback at the end of the session. So yeah, let us know what you think. And so going on to the next slide is, I won't go into too much detail. If you have interacted with the consortium, you would have probably met a lot of us, and going forward over the next few years, hopefully you will come to. Today in this call, we have 3 people, myself, Dr. Tristan Naidu. I recently completed my PhD in AI with a focus on natural language processing, and have a sort of stats background. And my main role in the consortium is to focus on building capacity and specifically related to modeling and data. We also have Catherine Forbes, who's the senior project manager and kind of keeps everything ticking along. I'm sure you've probably heard from her if you have interacted with the consortium. And then we have Dr. Gina Chandli, who I'm going to hand over to shortly. Before I do, I've posted a message in the chat, but just a few sort of housekeeping rules for the session, and this will extend to the other sessions too, but I'll sort of repeat as at the start of each session. So the first is that microphone and cameras are disabled for the session, but the chat feature will be enabled. So Catherine and I will be monitoring the chat. So if you have anything that you'd like to raise that isn't a question or sort of any technical issues, please post it there. If you have a question, please post it in the Q&A feature. And if someone's asked a question that you'd like to answer, please upvote it in the Q&A panel rather than ask it again. We're going to have a Q&A session at the end of the presentation, so we'll go through those and sort of pick the highest ranked questions to answer. There's also an option, or there may be an option, to navigate the slides yourself, depending on your view. To keep up with what's presented, if you see an option that says sync to presenter, please click that. We have, when we sent out the initial sort of advertisements for this, you would have noticed that you will receive a certificate for attending the session, but you need to attend the full session and complete a feedback form, which will include a policy question activity that Gina will get to in the session. And then the final note is that the session will be recorded. So yeah, please bear that in mind. Cool. So handing over to Dr. Gina Chandli.
Yeah, so thank you very much, Tristan. So yeah, as Tristan says, I'm Gina Chandli. My background is in veterinary medicine, and I have a master's in climate science, and I completed my PhD in 2023 in epidemiology, climate-related epidemiology, and I mainly use statistics and sort of machine and deep learning in the work that I do in epidemiology. So yeah, I'm going to be mainly covering the session today, and then Tristan's also here to help with the Q&A as well. So I just want to first of all welcome you all to the EDAM Capacity Building Programme. This is session 1 in our July series, and today we're going to be covering sort of an introduction to modelling and what a model actually is and how we can use them. We have about 40 minutes of lecture content, and then we're going to have a short exercise, and then we'll have time for questions at the end. And also, you know, if you have any questions about the exercise we ask you to do, you can also ask them then as well. And then followed by a feedback form that we're going to send you, as Tristan said, and information on how to attend your certificate of attendance for today. So here's sort of a bit of a roadmap of what we're going to cover today. So there's going to be 6 different sections. The first one is going to look at what is a model in more general terms. And then we're going to move on to what is modeling sort of specifically to epidemiology. Then we're going to look at sort of the different types of model that exist, how we can use them in practice, and sort of matching the right model to the right question. And finally, sort of their limitations as well, because no model is going to give you the full picture. And sort of knowing where they break down is as important as knowing how to build one. And then finally, we're going to look at sort of bringing all of this together to have a better understanding of how we can develop health policy questions that can be answered using modeling. So first of all, what is a model? So at its core, a model is a representation of a system. It's a simplification of reality. So it doesn't try to capture everything, just the part that matters for the question that you're answering. And so what that means in practice is that it's a set of assumptions encoded with algorithms or equations to help you capture how you believe that a system works. So a really simple example of this, and one that you may have used without necessarily even calling it a model, would be a line of best fit. So you have a scatter of points and you draw a line through them. And that line is your simplified representation of the relationship between those two variables. And it won't hit every point exactly, but it captures the overall pattern well enough to be useful. So another example, which is the diagram at the bottom there, would be sort of if you've ever drawn something like a flow diagram. So if you've ever been trying to sort of get your head around a problem, how maybe a disease is transmitted, or just, more generally in life, you may draw something like this with sort of like boxes and arrows. And what you're showing here is sort of variables and a direction of flow through those variables, which is, the representation of the system and how you believe that system works. So that's the essence of sort of every model that we're going to talk about today. Sort of however complex it gets, it's a simplification built on assumptions that is useful for a specific purpose. So models aren't some abstract sort of academic tool. We encounter them consistently across a huge range of fields. And here I've given, sort of three very quick examples, but of course this isn't an exhaustive list. One example that I'm sure we all use on perhaps even a daily basis would be the weather forecast, which is a very simple representation of sort of atmospheric physics to try and understand how our weather is going to behave in the short term. We also have financial risk modeling. So this is something that things like insurers and banks use to predict risks and losses and decide who to insure and who to give loans to. And then also we have things like crash testing. So today, more and more, we do this using computer simulations rather than sort of physical dummies in cars. And what all these very different examples have in common is that they're all doing the same thing, which is they're simulating a system, they're testing interventions or scenarios against that system, and they're using it to predict future outcomes. And that's really the value of any model, whether it be weather, finance, road safety, or as we're about to get into, sort of disease and health. So what is modeling in the context of epidemiology? So just to cover sort of what is epidemiology, it is the study of the distribution, patterns, and determinants of health-related states or events in a specified population. It's not a new field. It is cited to have dated back to the 1850s to John Snow, who was looking at cholera outbreaks in London and the famous Broad Street pump, which is still in London today. And if you ever want to go on if you get sick of the usual sites in London, you can go and see the Broad Street pump, which is still there today. It's quite a specific tour of London, but it is there if you want to see it. And what Snow basically did was he mapped cases and he traced them back to a single water source, which in this instance was this pump. And in doing so, he made one of the earliest arguments for a mode of disease transmission using patterns and data rather than prevailing theory at a time. So basically, he developed a model of how he believed that cholera was spreading in London and was able to map it back to this one water source. And they closed that pump and the cholera outbreak ceased. So in relation to epidemiology specifically, a model is just using mathematics, statistics, or computational representations of disease processes, populations, or health outcomes. And we're doing this to understand, explain, or predict how a disease spreads or how it could respond to an intervention. So it's the same sort of general idea as the last slide. It is this simplification of, a system, but it's just applied to disease and health. So before we go any further, it's worth sort of like pausing to take note of sort of some key terms, because these come up consistently in sort of epidemiology and in modeling, and knowing their distinction really matters for how we use models and how we interpret their results. I have to say, I sort of have to look up these terms probably like once a year. They also slip my mind, and this is by no means an exhaustive list of, you know, of all terms you come across, and I'm even going to use other ones today that also aren't included here. But I think that it's worth sort of talking about them a little bit sort of before we get going, and sort of like raising sort of some important ones. So I think important ones to pull out here are exposures and outcomes. So your exposure is the variable that may cause or influence the outcome. So something like a flood or a drug, and the outcome is the health event that you are measuring. So the disease, deaths, hospitalization. And then sort of in the cause and associations category here, as I've sort of lumped them in these three different, very broad categories. So this is an association. It's a statistical relationship between two variables, but crucially, it's not causation. And in modeling, most of the time, this is actually what we're looking at. Whereas causation is where one variable directly produces a change in another. And one of the reasons that so often in modeling we're looking at sort of an association or correlation rather than causation is because of something called confounding variables. So this would be a third variable that distorts the relationship between the exposure and the outcome. And age would be a very specific example of this for many diseases that we're aware of and that we come across. How those diseases affect sort of infants or children under 5 years old is very different to how they may affect, you know, more older people in our population, so people in their 70s, 80s, 90s. Finally, just sort of a few on model structure. So a covariate or a predictor is a variable you include to explain or adjust for variation in your outcome. So basically, that's sort of the modeling way of determining what an exposure would be. Instead, when you're fitting a model, you would call it a covariate or a predictor. And then finally, a parameter is the value that you want to estimate. So these are things like your regression coefficient or your rate, whatever it is that this value that you want your model to estimate. You don't need to memorize all of these today. It's sort of just here as a reference that you can go back to. And we're going to make all of our lecture material available to you afterwards as well. So this is something that you can come back to for a useful reference if needed. So moving on to sort of what are the different types of models. So broadly, they fall into three main categories. The first one being statistical models. So here you're looking at your more frequentist approaches like regression modeling, where you're fitting your data to a known statistical distribution. You also have your Bayesian approaches within that as well, which are built on Bayes' theorem. So this allows you to update your beliefs in the likelihood of a hypothesis based on your prior knowledge. Then you have your mathematical models. So these are your compartmental models like SIR or susceptible, infected, recovered models. These tend to work more on a population basis, but then you also have your agent-based or individual-based models, which are the same concepts of these compartmental models, but they're looking at sort of individuals or in sometimes called agents. And then finally, you have your artificial intelligence kind of models. So you've got your machine learning algorithms and your deep learning neural networks as well. We'll come back to where sort of all of these models sit in a moment, but I think it's worth flagging now that although I've separated these categories quite neatly here to show you, I think that in practice, often these elements of these can be blended in how we use modeling in epidemiology, but overall, they tend to be categorized into these three main categories. So before you choose a model type, there are kind of two questions that you always need to ask yourself. The first one is, what do you actually want your model to do? And the second one is, what information do you actually have available to you to answer that question? So these sort of might sound simple, but skipping this is probably the single most common mistake that people make in a modeling exercise. Sort of jumping to a method before you have a clear purpose and data is sort of like quite a common mistake and can cause big issues further down the line, and also can mean that you end up sort of wasting time because you realize either that your model can't give you what you want, or that you just don't have the information that you need to fit the model in a way that is going to be helpful. So because of these are so important, we'll sort of take some time now just looking at these two questions over the next few slides. So question one, what do you want your model to do? There are sort of like three axes to think about here. And again, I'm going to include some more terms. And I myself, like I said, I myself forget sort of the distinctions between these sometimes, but they're always good to sort of have in your mind the distinctions of what these terms mean. So the first one is do you want your model to be mechanistic versus empirical? And so what we mean by this, and the question that we're really asking ourselves is, where does the model structure come from? So does it come from theory about how the system works, or has it been learnt from your data? So a compartmental SIR model would be mechanistic. The structure reflects our theoretical understanding of how the infection spreads, whereas something like a regression model would be more empirical. So the structure is largely dictated by the data. You're basically saying, how well does my data fit this statistical distribution that I believe that is very close to what it's supposed to look like? Then the next question to ask yourself is, do you want it to be deterministic versus stochastic? So basically, how is uncertainty and randomness handled? Is there a probabilistic component such that the same input can produce the same so the same input can produce different outputs each time you run it? So deterministic models would give you the same answer every single time you ran your model, whereas a stochastic model would capture the randomness inherent sort of in real world processes. So every time you ran it, it would give you a slightly different answer to sort of account for the fact that the real world is very messy, nature is messy, data is messy. And then finally, you need to ask yourself, do you want your model to be inferential versus predictive? So what is the model actually for? Is it there to help you understand the mechanism and how your disease is sort of like working or spreading? Or is it there as a forecast to tell you what's going to happen next? These two sort of inferential and predictive models aren't necessarily mutually exclusive in practice. So some models are able to give you both. But I think what you're more interested in and what is more important to you in your modeling exercise will probably slightly pull your model design into one direction. So putting that together, here's sort of like roughly where each model type sits across these different axes, with deterministic to stochastic running from left to right there, and then mechanistic to empirical and influential to predictive as other dimensions. So you've got your compartmental models sitting on the mechanistic inferential side, and then you've got your statistical models like regression and your Bayesian approaches sitting on the more empirical side. And then moving towards the stochastic and predictive end, you've got, your more agent-based and individual-based compartmental models, and then which are mechanistic but stochastic. And then you've got your machine learning approaches, so things like random forests and XGBoosts, and also your deep learning models, things like neural nets. And these are sitting towards the more empirical, predictive, stochastic end of sort of like where models sit. This isn't a rigid grid. Plenty of models sort of like have blended properties, but it's sort of a useful mental map for placing a model that you come across and for understanding that some of these models do some of these things slightly better than others. And this is always going to sort of guide what model that you end up picking in the end for what you want it to do. So then we move on to question two, what information do you actually have available? So this differs quite a bit depending on sort of like the three categories that you're working in. So whether you're looking to do something statistical, mathematical, or something AI based. So for a statistical model, you need a clear hypothesis or estimand. So that just means the thing that you're estimating. So what effect or association are you actually testing? And you need to have sort of a good idea of that before you get started. And then you need a chosen distribution or family. So you need to have a statistical distribution that you believe best represents your outcome. So this could be something like a normal distribution or a Poisson distribution. You need your outcome and covariates clearly defined, including the confounders that you plan to adjust for, and you need an adequate sample size, ideally backed up by a power calculation for the effect that you're interested in. Then you move on, so we have mathematical models, where here the most important thing is that you need to have a model structure. You need compartments, you need equations, you need agent rules, you need parameter estimates, such as things like rates and probabilities. And these can be usually drawn from data or from the literature. And so basically in that, what you need to understand is you have these compartments and sort of how quickly or at what rate do populations or people move between these compartments. You need also an initial set of conditions and a time horizon. So what state you're starting from and what period you're simulating. And you need a calibration or validation target. So observe data that you can fit to this model or to check against. And then finally, for your AI approaches, the most important thing that you need is a large data set with sort of like values for every feature with very minimal missingness across the rows. And why you need this is because with a statistical model, you need a good amount of data because you need to know that your data is well represented by the statistical distribution that you think that represents your outcome. Whereas with machine learning or deep learning, you're not giving the model that. So you're giving your model sort of the least amount of information up front, and you're saying, here is all of my data. You tell me what the relationships are. You tell me how these things are related. And so obviously you need enough data for your model to be able to accurately learn what is really going on in reality. And so for AI-based approaches, data is the most important compared to sort of statistical or mathematical or across these three different kinds of approaches. So you also need labeled outcomes. So this will be so that you have sort of like a ground truth for your supervised learning techniques. And you need a train, validation, and test split so you can properly assess generalization. And also for this, you need enough computational power. All of these models can be quite, you can make them as complicated as you want. And certainly for mathematical models, some of them can be get incredibly large and incredibly complicated and need a lot of computational power. But particularly for AI-based approaches, they can be particularly computationally intensive. So it's good to make sure that you have the resources to be able to fit these models. So I think the common threads really across all three of these is know what you need before you start, sort of like not halfway through, so that you don't waste any time and you know that you have what you need to fit the model well. So once you've selected your model and you have everything you need, the next decision is to sort of how you're actually going to encode this model. So programming languages are tools that we use to process data, encode models, test performance, quantify uncertainty, and to generate predictions. And broadly, I'm going to sort of cover three categories here that we would use specifically to epidemiology. There are other programming languages. There are also non-English programming languages as well. There are quite a few written in Mandarin Chinese as well. But generally, for what we're using in sort of like the health epi-space, these are generally the three languages that are the most commonly used. So we have R, and R stand for Bayesian work, and this is well suited to your more sort of fitting your statistical and your mathematical models. And then you've got Python, which is a dominant choice for machine and deep learning. And you have C++, which tends to sit underneath both of these as sort of your computational engine for sort of performing high intensive operations where speed really matters. You don't need to be proficient or fluent in all three of these languages, but it's worth knowing which language tends to suit your type of work the best. I personally would always stay away from C++. It's sort of very complicated. And for most people, sort of R and Python will give them what they need. C++ tends to be something that you need or that you use when you want something very, very specific or very tailored, and you require heavy computational mathematical computations in order to achieve that. So in terms of actually where you're then going to write and run this code, modern languages come with packages that let you fit and test models without writing every equation from scratch. And that's one of the reasons that we tend to sort of use different programming languages for different model types. And it's because that's because that programming language sort of has a lot of that architecture already in place. It already has packages that are in place, which allows us to fit these models and test how well they perform very easily. And this is a huge time saver compared to even sort of like 10 years ago. So you can run your code directly into the terminal, or you can run them through integrated development environments or IDEs. So R is so for R, we would typically use something like RStudio. For Python, PyCharm is very common. And then also there are these sort of multi-language platforms that you can use called, with one by Microsoft called Visual Studio Code. And sort of a lot of people tend to use these approaches when they're doing sort of mixed work between R and Python. So data is crucial for any model, but as I already sort of said, especially for empirical work, because you're not giving your model all of the assumptions that you are in some of the other modeling approaches, and you're letting your model learn from the data. So the data has to be as good as you can possibly get it. And how you store and process that data really matters, I think, more than people often expect. We tend to encourage people to stay away from Excel because it's sort of genuinely quite unstable, particularly when you're working with larger data sets. So it's really worth knowing the alternatives that are available. So for tabular data, that's looking at, data where you've got rows and columns and it's presented in more a traditional table. CSVs work fine for sort of your smaller data sets, which would be sort of a few thousand rows to even tens of thousands of rows. They tend to perform relatively well in. But then I think once your data set gets into the millions, it's sort of good to consider other options, such as an RDS, which is R specific. But there are also other options for different programming languages as well. And then for spatial data, you would use something like a shapefile or an SHP file. So this handles more vector data. So you're looking at your polygons, your points, and your lines. You also have raster format, which handle gridded data, and your netcdf files, which handle multidimensional arrays, which tends to be more suited towards Python. And this is typically what you see for sort of your climate and remote sensing data, but also sometimes for spatial health data, you can also sometimes find that some data will be stored in sort of shape files. So the right choice really depends on your data size and the structure and what programming language that you want to work in. But it's really important that you store your data correctly to make sure that the data is safe and you're not going to end up with data loss or corruption. So how can we use models? So we want our model, so what we want our model to do and what information we have available, we've selected sort of a broad category of models. And so now we need to know the exact model type, because so far I've sort of talked about broadly what kind of model types there are, but of course within these categories there are much more specific models. And how we use and interpret a model really depends on what outcome we're after. And this table again is sort of giving you a bit of a quick reference of that. Again, it's not an exhaustive list, and some of these models can do different tasks as well. But it's sort of to get you thinking about sort of this idea of thinking about what your model to do, what do you want your outcome to do, and then selecting a model that is appropriate for that. So sort of just to walk you through a few rows here for your sort of R0, RT, and sort of epidemic peaks. So you're looking towards, excuse me, transmission. We lean on more of the compartmental models because what we want to capture here is transmission dynamics in a mechanistic way. For outbreak risk, we're often looking at things like statistical approaches, as statistics helps us to quantify the probability of an outbreak sort of taking off or fizzling out. Our short-term forecasting is another place where statistics can do a lot of that work. So looking at your short-term time series methods like ARIMA, and these are often preferred over your full mechanistic models where near-term accuracy matters more than capturing mechanisms. And then you've got your spatial structural models, and these come in really handy for sort of hotspot mapping because they represent spatial autocorrelation really well, and they account for these in the model. And then you've got your machine and deep learning models, and these are really more used when you want to understand sort of complex patterns in large data sets, and particularly work very well with prediction as well. So if that's what you want your model to do, we often move more towards these approaches. So really the takeaway here is the outcome that you care about should drive your model choice, not the reverse. And the point of this slide isn't really, to memorize every row. It's like when we went back to sort of those definitions at the beginning, it's sort of to get you in the habit of starting from the question and letting your question point you towards the model type rather than the other way around. Sorry. So this is an important slide, and I'd say it's sort of the slide to remember, even if nothing else sticks today. I think what I'm trying to show here is that models are powerful, but they're not always the right tool, and it's worth being honest about both sides of that. Excuse me. Sometimes you just sort of don't need a model, and that doesn't mean that your question that you want to answer isn't incredibly valid and very much needed. But sometimes we don't need a model, and that's okay. And sort of things where you don't need a model would be to do something like to visualize a trend. So to look at a line chart sort of over time often tells its own story. To compare rates between groups, sort of when you need to do that, a simple ratio would suffice. To summarize what happens, we can use descriptive statistics to answer a lot of those questions perfectly well. To calculate a simple proportion, a spreadsheet sometimes can work sort of much better than a model, just to sort of visualize it in a tabular form. And then finally, to communicate descriptive findings, tables and figures are needed rather than sort of simulations. And equally, there are things a model can't reliably do. So it can't prove causation for observational data. Models can suggest, they can't confirm. And that goes back, right to the beginning, to those definitions that I showed you, where I said, most of the time what models are doing is they're looking at associations, not at causation, because causation is always, it's often much more complicated than that. It can't reliably predict far beyond the range of your data, so extrapolation amplifies uncertainty rather than resolving it. It can't replace missing or biased data. And in other EDAM sort of sessions, we've talked about this garbage in, garbage out sort of approach. And that applies just as much to sort of sophisticated models as to simple ones. The better your data, the better the model is going to be. And it can't capture behaviors that it wasn't built, that weren't sort of built into its assumptions. So what you don't show your model doesn't see, and your model isn't going to learn. And it can't tell you which intervention is quote unquote best in some sort of absolute sense. That requires value judgments that a model just can't make. And I think it's very important to remember those last two, because these are two things that we're going to talk about tomorrow when we look at this difference between artificial intelligence and human intelligence. So we're sort of remembering this idea that models can't learn things that we don't tell models. They can only learn the assumptions that we give them. And also, often human judgment is always required in any model that we build. And also this leads on well to my next section, which is looking at the limitations of modeling, which obviously some of them I have just covered there. So I think something to remember whenever we're using modeling is that biology is inherently stochastic, and our data are always imperfect. Two people can get a disease and on paper look exactly the same in every way. They can be, young, healthy, no pre-existing conditions, and one person could be asymptomatic and one person could die from that disease. And sometimes there is no sort of rhyme or reason to understand why that is the case. And it is just the stochastic nature of how nature and biology behaves. We try to account for this using uncertainty in models, but of course it can't account for everything. There are two main ways that we try to account for uncertainty in modeling, and the first one is using stochastic simulations. So we run the model thousands of times to try to capture the random variation in the outcome, rather than relying on a single deterministic run. And then also we have things like sensitivity analyses. So we systematically vary your inputs to see where your conclusion holds up and where they break down. And then we can hypothesize why potentially that might be the case and discuss that further. But there are things that even these tools can't address. Structural assumptions, for example, if your model is missing something like an age structure or a mixing pattern or waning immunity, no amount of simulations is going to recover that. It simply wasn't there to begin with, and that goes back to the same idea that models can't learn something that we don't tell a model to learn. Another one would be behavioral feedback. So people react to an epidemic and to a forecast about an epidemic in ways that are generally very hard to encode. We have always been and will likely continue to always be incredibly poor at predicting human behavior. Humans are inherently unpredictable in the way that we behave. And finally, early outbreak unknowns, which is always an issue in modeling. Parameters like R0, the infection fatality ratio, and the generation time aren't pinned down before the data exists to estimate them, which is precisely when decisions are most urgent. So for new diseases that we've never seen before, that we don't have past outbreaks or literature that we can go and explore how this disease has behaved in the past, we just don't know those things. And unfortunately, there is a point where we have to wait for more people to be infected, and unfortunately for more people to die, to have an understanding of how we can estimate these parameters. And so often early outbreak models, particularly for novel new pathogens, tend to be very unpredictable and tend to not perform anywhere near as well as models for diseases that are very well established or that were created later on in an epidemic. So that's really sort of like an honest picture of modeling, a generally very powerful set of tools with some real and very specific limits. And I think knowing both sides of that can make you a really good user of models. So bringing it all together, sort of looking at policy questions and how we can develop policy questions that we can solve through modeling approaches. So I'm going to walk you through a kind of like a bit of a pipeline here from left to right. So we can start with our policy question, and this can be very sort of vague and broad. And here I think the one I give is sort of, should we introduce a new vaccine? It can start as broad as you want it to begin with. And then we need to narrow it down into an answerable outcome. So sort of like using the vocabulary from the earlier slides, looking at things sort of like incidents or something like that. We need something to fit our model to. So we need an outcome, and it needs to be measurable in some way. There needs to be information or data somewhere where we have sort of calculated what this outcome is, and we've written that down and documented it. So narrowing it down to a measurable outcome. So cases averted, hospitalization, something like that. And the next step is then to define your exposures. So you need to sort of list every variable you can think of that you think could drive this outcome, plus any potential confounding variables that you think could distort this relationship. And you then need to think about sort of, is there data available on these? So is there data available on all of the different exposures that you think are important? And is there also data available on the confounders? And if there isn't data available, then you need to make sure you have a very specific set of limitations that can accompany your model, where you can say, okay, let's say we know age is important, but we don't have that information, or we know that sort of wash was important, but we don't have good enough data on wash. So you can be very upfront about what your model does well and where your model maybe doesn't do as well. And then we move on to sort of matching the outcome to the model type. So as we've already talked about today, and as we've already looked at today, making sure that we select the right model, and a model that can sort of answer the outcome that we're interested in. And then sort of finally, we look at sort of like the programming language and the tools and the packages that is going to make our life easier. So we have our model, we have our data, we know what we want it to do. Where is the best place to encode this so that I'm going to have the most options of sort of like how I parameterize my model, and how I'm going to test for uncertainty, and how I'm going to visualize my results, things like that. So this is sort of like working you through an example here. So the question is, should the Ministry of Health target cholera vaccination to specific worridas ahead of the rainy season? So that's your policy question. It's relatively broad. You moved then to thinking about your answerable outcome. So for something like this, you'd be looking at predictive cholera cases by worrida over the next 3 months, because you're thinking about things seasonally. So you'd be looking at things every sort of 3 to 4 months. Then you want to define your exposure. So we've talked about the rainy season already. So you want to think about rainfall and water source access, prior case count. So are people already sick in that region? And also population density. So if there aren't people there's not people there to get sick. You don't have, a wide susceptible pool to being infected with this disease. And then also other things you might want to think about is sort of sanitation and existing vaccination coverage as your confounders. So how a population is going to be impacted by the rainy season, and how cholera might spread is going to be confounded to the fact of, have they recently received a vaccination? So are people immune, so they were never going to get the disease anyway? And also, with cholera being a waterborne disease, someone having access to, say, a toilet and an ability to wash their hands is going to be at a far lower risk of cholera, no matter if it's raining or not raining. And then we think about our model. So for this, we're looking at things on a spatial scale, on a spatial temporal scale. So spatial statistical models can be really good for this, to find hotspots, or a compartmental model so that we can test different vaccination scenarios, because that's the question here about targeting cholera vaccination. We need historic cases by worrida, rainfall, water source data, and population, and vaccination coverage as well. And then thinking about the tools. So for something like this, if we wanted to fit a spatial statistical model, we would use R, as we've said before. And you can use things like INLET or RSTAN to sort of fit these spatio-temporal models, or you can use some of the compartmental packages that are available if you wanted to test your different scenarios. So now we're just going to move on to an exercise where basically we want you to pick a policy question that is sort of relevant to your own work. Obviously, you don't need to say this out loud, because you can't say this out loud. We want you to just write this down for yourself. And we want you to think about sort of, what is that policy question in one sentence? Define a measurable outcome. So what can be an outcome of your model based on the policy question that you're interested in, and then think about sort of like different model types, and what model types might be good for your outcome that you're interested in, and what data that you would need to answer this policy question. So think about all of the risk factors that would affect your outcome, and also thinking about any confounders as well. And obviously, you don't need to list where you would get this data. You don't need to say if this data is available. It's just to get you thinking about what kind of data you would need to be able to answer this question by using a model. So we're going to give you 5 minutes. Yeah, we're going to give you 5 minutes to kind of just have a go at that, because as I said, you're going to need to submit this with your feedback in order to get the certificate of participation. So if we give you 5 minutes now to get started with this, and obviously if anyone has any problems or any comments or concerns or want to ask any questions, we're then going to have an FAQ session afterwards. So you can ask any questions that you have in the FAQ section. So I'm going to stop talking now and give you 5 minutes just to sort of have a think about this. We're going to give you all 2 more minutes. We're going to pick up again at 11:45. So thank you, everyone. The first thing I'll just raise, I can see that some of you in the chat have been asking about where you put your policy questions and the answers that you've given, and it's great to see that so many of you are doing that. That's wonderful. So we're going to have a feedback form that we're going to give you, and we'll give you a link to this sort of right at the end. So we're going to do FAQs now, and then we're going to give you this feedback form. And within the feedback form, there'll be information just about how you enjoyed or didn't enjoy, what you didn't enjoy about today that you can give us. And then at the end of that form, there's going to be a place where you can just copy what you've written into the form. So it'll be very obvious when you get the feedback form. So just make sure that you have whatever you've written, that you have that somewhere on your computer, and then we're going to give you a feedback form where you can just copy that and paste that into and submit it. And don't worry, we're not timing you, so you don't need to do this in sort of like 10 minutes. You'll certainly have, for at least till the end of the day to submit this. We're not going to be sending out the certificates of attendance, sort of 10 minutes after this, because we'll have to go through them all. So don't worry too much about doing it, immediately. But if you want to, that's also encouraged. So yeah, moving on. This was just a little thank you. So I'll say this one now. So that does bring us to the end of session 1. And so just to sort of have a little recap there, we've covered what a model is and what modeling means specifically to epidemiology, the different types of model and how to sort of choose between them, and how to match models to sort of your question that you're asking and the limitations in that. And I just want to thank sort of everyone for joining and sort of for your participation today. It's been, fantastic to see so many people here. So now we're going to move on to the questions. We have some FAQs here, but people have posted some questions. So obviously we want to make sure that we answer those ones first. So I'll just read out the one that maybe has had the most upvotes. So someone has written, NQ, thank you very much for your question. You've written, in practice, how do we decide when a surveillance data set is good enough, in bold text, to build a model, given that routine health information systems often have missing data, reporting delays, and changes in reporting completeness? If I sort of have a go at answering this, and then obviously Tristan can jump in, and if he thinks sort of I've missed anything, I think, knowing if your data is good enough is a great question. I think that it's sort of very much like how long is a piece of string, and it's there never, unfortunately, is sort of a set data set that is perfect. I think that some of it depends on your model type that you want to pick. So for something like a machine or a deep learning model, it's important that you have a relatively decent amount of data. I would say, from my experience of fitting machine and deep learning models, you need in the thousands, not the hundreds. That would not be enough data. And so I think that whereas if you wanted to fit something more mathematical, where you're giving your model far more assumptions up front, and what you actually just want to do is test if these assumptions hold up, you probably could do that with a lot less data, potentially, hundreds of data points, rather than sort of like, thousands, tens of thousands, millions. Of course, data missingness, reporting delays are a huge challenge. And that's something that Tristan's going to talk about in session 3. He's going to talk about sort of like how you can better account for, like you said, the vast number of issues that there are in data sets. And sometimes you just can't account for them. And you have to write that in your limitations, the fact that, you just couldn't account for the fact that the data didn't exist. Do you think I've missed anything?
No, I mean, I think it's spot on.
Yeah.
Probably just to add is when you fit, in all these cases, no matter how many data sets you have, you need to fit the model and see what comes out and sort of look at any accuracy metrics you have. And Gina sort of alluded to this too, is that with machine learning or deep learning models, you're sort of learning relationships, whereas the mathematical models, you're defining those a bit more sort of stringently. So you do need just a lot more data.
Cool. I hope that answered that question. So moving on to Samuel's question. Thank you very much for posting your question. How many records of data is needed for machine learning to develop a model? Does it affect the accuracy of your model? So yes, I guess we've alluded to this slightly. I think that it's particularly important for things like machine and deep learning that you have enough data, as we've said, because you're asking your model to learn everything just from the data, rather than giving it sort of like some information up front. And a problem that can happen with machine and deep learning models, and a criticize that they get quite a lot, is that they're prone to something called overfitting, which basically what happens is that if you give a machine or a deep learning model some data, it's going to find something because that's what you've asked it to do. But if it can only find one relationship and it can't find anything else, it's going to be like, oh, great, that's the relationship. And it's going to sort of give you predictions based on just that relationship. And as we know, diseases and how they transmit is very complicated. And one of the issues with these overfitting data set is when models are overfit, is that actually they often perform incredibly well when we look at traditional performance metrics. So if we look at something like area under the curve or R squared, they often have huge numbers. So they look on paper like they're performing really well. But then when you look at something like the uncertainty, their uncertainty values are really, really narrow because what they've learned is only very, very narrow. And that's a good way of testing if your model is overfit, is to look at the uncertainty of the model and see how narrow that uncertainty is. Because the problem is once you show that model data that it wasn't fit on, it's obviously going to perform very poorly because it's not capturing the full dynamics of a system. It's just capturing one tiny little relationship that it was able to find in your data. Yeah, nothing to add. Okay. I hope that answered your question, Samuel. So finally, John also submitted a question, and thank you very much, John. So John's written, could you clarify the difference between predictive and inferential models? Yes. So I guess I can go back to my slide on that, which was somewhere. There we go. So yeah, looking at inferential to predictive models, what you're basically asking in that instance is what's your model for? So what is the purpose of your model in terms of when you have fit your model, what do you want it to do at the end? And so an inferential model is telling you about your outcome, is telling you about its relationships to the exposures and the parameters and the covariates that you've put in your model. It's telling you about those relationships. So let's say you have a disease and you want to better understand how it relates to its risk factors. You would want an inferential model to tell you that. Whereas a predictive model is where your outcome, that what you wanted to do, you're not as interested in sort of like how all of these things are related. What you're interested in at the end is to be able to say what's going to happen in the future. So you're like, okay, well, we know how these things behave. We know that they're related. We know the relationships. What I actually want is a forecast for the next sort of like 3 to 6 months. And in those instances, things like machine and deep learning models actually come in really well because they tend to be quite powerful predictive tools, but they're not as good as telling us about sort of what these relationships are underneath. So yeah, I feel like that answered that question. I don't know if you want to add anything else or not.
No, I mean, I guess just to add with the machine learning and deep learning tools, this is kind of why they're called black boxes at times. It's because it's quite hard to understand. But there are sort of tools that are coming up that help to understand them slightly better. Which is sort of an interesting development or area that people look at.
Yeah, for sure. Yeah. Okay, there are some FAQs, but maybe with time, I'll go to the feedback. Yeah. So yeah, there is going to be a space in the feedback form where you can say if there was any questions that you had today that we weren't able to answer. There is going to be a little section for you to write questions, and this obviously will be able to guide us in any future training sessions that we do. So if you all had a question about something very similar and we didn't address it very well, then obviously that's something that we would look to address in future training sessions. So yeah, just looking at the feedback here. So to obtain your certificate of attendance for today, you needed to complete the registration, and you needed mainly to do that just so we have your email address and everything that we can send the certificate of participation to. You need to attend the full hour, and then you needed to complete this feedback form. And within that feedback form, like I said, this is where you'd be able to submit your policy question and how you would answer that policy question with a model. And then once we've got all this and we've got everyone's email addresses back for who submitted their policy questions and their feedback forms, we'll then look to email you the certificate of attendances. We're running these seminars for the next few days, so we're going to be quite busy. So if you don't sort of get the certificate this week, don't worry, it's coming, and we've not forgotten about you. So obviously, if you don't have a second device to, yeah, Tristan has given the link as well in the chat to that feedback form. So yeah, if you don't have a second device to use the QR code, you can just click on that link and it should work just fine. Maybe if we can see some thumbs up to know that people can access that feedback form. I mean, if not, obviously people can always contact us and say if they're having, okay, I'm seeing a thumbs up. That's wonderful. Thank you very much. Lots of thumbs up. Thank you. That's helpful. So yeah, I think the one last thing that we wanted to cover today is that, like I said, so this is going to be a series. We're running one today, tomorrow, and then Thursday as well. And it's not too late if you also would like to come to session 2 or session 3. These are the QR codes to join these sessions. If you sort of don't have enough time or anything to get the QR code now, maybe if you sort of screenshot this slide or something. And so session 2 is going to be tomorrow. That's going to be at 11 a.m. Ethiopian time. And we're going to be looking at how can artificial intelligence emulate human intelligence. So looking at the differences between sort of like even some of sort of the modeling approaches that we've used today and how we train models and how they think can be quite distinct to how us as human beings think. And then session 3, that's going to be on Thursday, is going to be looking at how to identify and solve issues with your data. And again, that's going to be at 11 a.m. Ethiopian time. And as we talked about there in the Q&A, we're going to be looking at, how do we account for the fact that data is imperfect, and sometimes we just don't have enough data. Sometimes we have missingness. Sometimes we can have difficulties in mapping sort of places to place names and things like that. And how can we account for this the best that we possibly can through coding and through using things like R and Python and stuff like that. So yeah, we would also really love to see you in those sessions as well if you aren't already coming to them. I think that is everything that we wanted to cover today.
Just one more thing to add. We've noticed a lot of messages in the chat about the recording and the slides. The slides and recording will be made available after the session, and the recordings should be emailed to the address that you signed up with, and we will make sure that the slides are available. And then again, just to highlight, the link to the feedback form is in the chat. So you might just need to scroll up a bit to see it, but it is there.
Yeah.
Cool. I think that's all.
Yeah. So I just wanted to say again that we've had excellent attendance today. It's been fantastic to see so many people here, and we really hope that this session was useful. And yeah, it would be great to hear your feedback. It would be great to hear what you liked, but also what you didn't like. And if you have any ideas for future trainings, that would be really helpful. And yeah, I just want to say again, on behalf of the whole EDAM team, thank you so much for joining. And we're happy to give you back 2 minutes of your day. So yeah, hope everyone has a great day going forward.
Thanks, Brian.
Thank you.
Cheers.